Okay, tonight's homework was problems 1 through 3. I'm going to ask you to pause at some points just to kind of see if you can do this. So it says a sample of helium has a volume of 3 liters. So volume 3 liters when the pressure is 500 torrs. What volume, so we're looking for question mark liters, does the gas occupy at 300 torr? So here's our new pressure. Okay, so when we're doing our GAW, we're going to draw, so we've got a sample of helium. I'm assuming that it's in a closed container because it only takes up a certain amount of space. It is a 3-liter space that it takes up, and it is at, you know what, let's undo that real quick. Oops. Let's draw that balloon one more time. I'll show you why in a second. So this is 3 liters, and it's at 500 torr. So the pressure is equal to 500 torr. So if I'm drawing my particle picture, I'll notice that the temperature doesn't change. I'm going to have a few of these bounce off, and I'll tell you why in a second. So I've got my particles that are moving inside that balloon. A couple of them are against the wall. Now, the balloon's either going to get smaller or it's going to get bigger. Okay, well, I should remember that pressure and volume, just from today, is an inverse relationship. So if the pressure is now 300 torr, or torr, what's going to happen to the volume? Well, the pressure went down, so it went from here to here, so the volume should be bigger. So the volume is going to be bigger, which means now on my particle picture, only one of them is hitting the sides of the wall, and there are 4 particles out here. And I could show too that there's air on the outside that's kind of pushing. And again, not super duper important, but we could have a key. This represents not air, but helium particles. And again, I guess we probably should have made the air particles a different shape. So let's make these stars. Okay, so again, relationship here. Here's my T0, here's my T0, and here's my T1. Here's my T0, and then here's my T1 because we reduced the pressure on that graph. Okay, so there I go. So now I can say for every 3 liters, there is 500 torr, and then for every blank liters, there is 300 torr. So I divide by a number. So to go from 500 to 300, is going to be divided by 1.67. And because this is an inverse relationship, that means that I do the opposite and I multiply by 1.67 here. And I get an answer of 5. Which you can kind of take a look and see, oh, this went from 5 to 3, which means that if this is the inverse, this should go from 3 to 5. I don't really need a calculator. I don't really need to see if I can see that. Okay, so there's problem number 1. And again, that kind of matches reality because we said that the balloon should get bigger. Okay, let's try problem number 2. It says at a pressure of 100 kPa, a sample of a gas has a volume of 50 liters. Okay, so here's my P, E, and then here's my V, and then it says what pressure, so the P is what I'm looking for, does it exert when the gas is compressed? Here's my second V. It's going to go down. So again, pressure, volume, inversely related. So if I were to draw this in my given, okay, I've got a pressure 100 kPa, and I've got a volume of 50 liters. Second picture, the volume went down. So the volume, the balloon got smaller. So now my V is 40 liters. And my pressure is the thing that I don't know. Now that pressure is going to be in kPa when I'm done though. Okay, so now let's figure this out. All right, so I got to show that the volume went down. I did that. And what should happen to the pressure? Well, the volume went down, which means that if this is my T0 and this is my T1, then if the volume went down, then I'm talking about this to this, right? Because this is going to be a smaller number than this. So that means that my pressure went up because my V went down. Okay, so now in my pressure I've got 100 kPa and I got to show that the pressure went up in my picture. So again, temperature was constant, so I'm going to show a couple of them bouncing off the wall, moving in random patterns, and then my pressure went up, and so I'm going to show still 5 particles, but this time 3 of them are bouncing off the wall. Okay, because the pressure went up. Now that I understand conceptually what's happening, now I can go ahead and try to solve this. So I can say for every 50 liters, there is 100 kPa. And then for every 40 liters, there is blank kPa. Okay, so this went down by 1.25, which means that this is going up by 1 1/4. So this will be 125. Again, as the volume went from big to small, then the pressure went up. It's going to be more likely to collide with the sides of the container because the walls are closer. If you think about the Star Wars, New Hope, the very first Star Wars movie, Episode 4. You know, remember when Luke and Leia and Han and Chewie were all trapped inside of the trash compactor? The walls started to close in on them. There was a lot less space. The air was being compressed inside of there. Everything goes back to Star Wars. 375 milliliter sample of nitrogen. So here's my V. Is kept at a constant temperature. So I know that T is a constant. It has a pressure of 1.2 atmospheres. What pressure, so I'm looking for my P, is going to be some number of atmospheres, does it exert when it's compressed to 125 milliliters? And again, I'm going to draw my graph real quick over here. P and V, I remember, are inversely proportional. Let me draw my 2 pictures. Here my T0, here's my T1. This time I got 375 milliliter sample. So my volume is 375 milliliters. And it has a pressure of 1.2 atmospheres. I'm not going to draw any particles yet. And I got it compressed a little bit. Now, a lot of bit. Now the volume went down quite a bit. So now my V is 125 milliliters. It went down quite a bit. And they want to know what's my pressure, and that'll be in atmospheres. So some number of atmospheres. Oh, I didn't really make my balloons big enough. Let's see if I can rectify that. Oops, maybe not. Let's see, can I make this a little bigger? Maybe not. All right, so let's just pretend here for a second. So I'm going to throw in 3 particles. Well, one's bouncing off the walls, and now I've got 3 particles inside of here. Are they more or less likely to be bouncing off the wall? Well, they're a lot more likely to be bouncing off the wall. There's a ton of pressure inside of that balloon when I decrease the volume on it. So let's go ahead and, for every 375 milliliters, there is 1.2 atmospheres of pressure. Let's go back and take a look at our graph here. So my volume originally was pretty big. It was at 375 milliliters, which is way up there, let's say. And what happened then, I went and made the volume a lot smaller, which would be somewhere down here. So what happened to the pressure when the volume went? So the volume is going down, and the pressure is going up. Okay? So again, conceptually understanding it and mathematically understanding it. The graph helps to explain why this happens, and it helps us to predict what's going to happen the next time. So now for every 125 milliliters, there is blank atmospheres. Okay, so going from 375 to 125 would mean that I'm dividing by 3. So the volume went down by a third, which means that the pressure is going to go up by 3. Okay, so this will be 3.6 atmospheres of pressure. So I hope that you're starting to see the relationship between these two things that are inverse, pressure and volume. Okay, we'll practice some more a little bit tomorrow. We're going to draw some more PPs. I'm hoping that we all got this down pretty soon. Have a good night, guys.